The one thing I want you guys to recognize is that this program does a good job of kind of, when questions are really elaborate, they walk you through all the necessary steps that you need to kind of create using old algebra information to end up making a conclusion, okay? But when you get to, again, the end of course exam, they're going to say, provided point A equals -5, -6, B is 1, -3, D is -8, 0, E is -2, 3. Justify why triangle ABC is turned into triangle EDC. And they do not walk you through every single thing that you need here to be able to do that. Does that make sense? And that's as you get through into more advanced mathematics, it is no longer going to be, here is a style of problem, here is the practice of doing that style of problem, and do it repetitively over and over and over again, like you've done since the 3rd grade. Okay? It is going to be, here is a particular unique question in regards to the questions that come before or after it, in which you have to pull from different areas of mathematics to come up with a conclusion. Okay? And it's not as linear as a lot of the things that we are accustomed to and the things that we like, right? Most people like to be able to say, okay, this is how I do this process, step by step by step, to get an answer. Okay? Beyond this class, and to be honest with you, with a lot of stuff that we're going to do in this class, you're going to be pulling from different areas, okay? And trying to put 2, 3, 4 different concepts together to make a conclusion, okay? And this question might be a little bit different than the next one, which will be different than the next one, okay? So I just want you to understand that, okay? The first thing I ask you to do is graph this thing and match the graph. So at this point, hopefully we're all able to do that. That ends up being the graph that we get. The next part they ask you to do is to determine slopes of AE and BD. Slopes of AE and BD. The slope formula, M equals y2 minus y1 over x2 minus x1. That's your slope formula. y1, y2, and x1, x2 come from ordered pairs. Okay. I think it's also beneficial to be able to recognize formulas in different formats. You might be presented with that. Okay. That means the exact same thing. Okay. Change in y, or difference in y, divided by difference or change in x. Okay. I get a lot of students in more advanced math classes or even a physics class come back to me and ask me, can you help me do this? And I ask them, what's the formula? Write the formula down. And they write it down. I say, okay, now what does that mean? And then I don't know. So we rewrite the formula to something that they learned back in the 9th grade or 10th grade in geometry or algebra 1, and then it makes the concept that they're talking about so much easier. All right, so they see delta y or delta x. They ask, what does that mean? Well, rewrite it as y2 minus y1 or x2 minus x1, and it makes it so much easier. Okay? We've done this before, where the distance formula is a hard formula to remember. But if we realize that it's, rewrite it as the Pythagorean theorem, it's a lot easier. Okay? So start looking at formulas and recognizing the varying ways that it might be presented. I would hate for you to get to some test, whether it be the enforced test, ACT, SAT, college entrance exam, and they give you a reference sheet or they give you a formula to help you on that particular problem, and this is the formula that they give you, and you've never dealt with it, or you say, oh, I don't need that one. I already know the other one. Okay, it's going to be very important as you move on through your high school that you can recognize varying formats of the same formula. Now, what I want to show you is that on a line, because they want the slope of AE, right? On a line, it does not matter which points you choose to determine slope. And the reason I want to show this to you is because inevitably every year somebody asks me, I don't know how to do slope, I don't understand which points to choose, so hopefully maybe this will explain it to us. I'm going to look I'm going to change this point C. I'm just going to write it as x1, y1. And this one here, F, we'll name it x2, y2. All right. The logic of finding the slope, and you were taught this in Algebra 1, is that you can take these points anywhere you want them to go, and you should be able to find the slope of the line that connects them, or the segment that connects them, right? So no matter where these 2 points are, is the line AE always the same line that intersects them, or that is created by those 2 points? Even if this one's down here, right? Even if they flip-flop kind of relationship to one another. This one's now below x1, y1. And to prove this to you, I'm going to ask GeoGebra to, I'm going to tell it to do some calculations, okay? So this point here is F, and this one over here you see as I start moving that one, it changes C, right? So the bottom one's F and the top one's C. So what I want to do is I'm going to create a formula here for doing slope. So I know slope in general is going to have a numerator and denominator, right? I want to take the y value of that point right there. Okay, so the way I do this, I say y, the y value from point F, and I'm going to subtract that from the y value of point C. Okay, so that's how I tell us with GeoGebra to take whatever these y values are right here, the negative 1.81 and the negative 3.82, it's going to subtract. We're then going to do the same thing for the x values. So I'm going to say the x value of F minus the x value of C. And when I hit enter, it's going to give me a number. And that number is 3 right now. If I hover over that 3, you see that formula is still in the background, right? Now, to prove to you that the slope does not matter which 2 points you choose, pay attention to what happens to that 3 as I move these points around. Because right now, and it's really not taking the numbers that we see, it's taking the infinite number of decimal places that we're seeing here, because these really aren't really cute numbers, are they? Or locations in the XY plane. But it's taking that and doing the algebra with them, subtracting them and dividing them. But no matter where I move those points, okay, what happens to that number right there? Does not change at all. No matter where I move x1, y1, no matter where I move x2, y2. Okay? Now, for us, the hope is that maybe we move those points to, hopefully you realize that's probably a good point to choose, right? Because that number, that group of red numbers right there, is a lot nicer looking than that one, right? And then maybe I change this one here to right there. And do I still get 3? Okay? So because that slope never changed, regardless of the 2 points that I took off of that line AE, the slope never changed. One of the main concepts that you talked about in Algebra 1, not just being able to find the slope, but you should have talked about how the slope of a line is constant. The slope of a line never changes, okay? Because basically what it is a set of directions to get me to move away from one of those red points, okay, to move away from that line and then get back to that line. Okay, that's what rise over run is, right? Okay, I should be able to go from that bottom red point, rise 3 units, and then run 1 unit to the right, and I should get back to the line, correct? And that idea means that no matter where I do that, okay, if my points are there, okay, I should be able to essentially rise a multiple of 3 and a run multiple of 1 to get from x2, y2 to x1, y1. Okay? As you're doing this problem, I think the most logical thing for you to do is not to choose any of these other points that are in here. Even though some of these other points were really nice values to choose, don't you know that A is on line AE and E is on line AE? So use those two. Okay? But on an end of course exam, maybe you're not provided with those two. Maybe you got to do something else. Okay? You choose a different set of points. But when I find a slope of AE, I'm going to go y2 minus y1. So again, I'm looking at that point and that point. Negative 6 minus 3. and then negative 5 minus negative 2. So that's going to give me what? Negative 9 over negative 3. Negative divided by negative is a positive. So I get positive 3 for that slope. I'm then going to do a slope of BD. So looking at those two, so I'm going to go negative 3 minus 0, and then 1 minus negative 8. So it gives me negative 3 over 9, and that reduces to negative 1/3. Okay. Somebody in the last class said, how did you know to subtract straight down, negative 3 and 0? I didn't. It's just the way I do it. Somebody could have said 0 minus negative 3. So they could have said, we're going to actually travel and find the slope from D to B. So 0 minus negative 3. And then go negative 8 minus 1. Well, what's 0 minus a negative 3? Positive 3, right? Negative 8 minus 1 is negative 9. Does that still reduce to negative 1/3? Yeah. Okay. Basically, what happens is you reverse the top, and you reverse the bottom. It just takes the negative sign and puts it in the bottom instead of the top. Okay. Ultimately, what that means to us visually is we're either going from A to E, finding that slope left to right, or we're going from E to A, finding that slope, but they should be the same. Okay, so that's critical for some things that we want to do later in this problem. If these two things, these two slopes, have that comparison to one another, okay, because this is 3 over 1, right? Are they reciprocals? Are they opposite sign? So what's that tell you about AE and BD? They're perpendicular, right? Opposite sign reciprocals for slopes tell you that the lines are perpendicular. So when I go to my picture, we can put right angles in here, which is going to be useful for us because they want us to classify, or sorry, not classify, but justify that these two triangles are congruent. So that's necessary. It's useful. Okay. I'm going to write here that slope of AE was 3, slope of BD, negative 1/3. The next part says develop equations for AE and BD. All right, so I told you yesterday, if you struggle with this, you don't remember from Algebra 1, watch the 2 videos. In the 2 videos, or I guess 3 videos, in every one of them, they provide you this thing here. Okay? You've seen it a little bit in Algebra 1. Okay? I talked to Ms. Cole the other day, she said, yeah, we deal with it. Okay? You're going to see it a lot in this class. You're going to go back to Algebra 2, and you're going to use it a lot in Algebra 2. In the first 3 or 4 weeks of college algebra, we use that thing again. When you're in science, you use that thing. Okay? You go to a lab report where you find the line of best fit. You guys ever have to do that? Line of best fit, line of regression. You're going to use that formula to come up with that equation of that line. So that is going to be kind of one of the top formulas you want to take from a math class in high school. It is the exact same thing as y equals mx plus b. Okay, if you remember that phrase. We'll talk about maybe if we have time where y equals mx plus b comes from this thing. Okay, but in order to do this, we need to realize that the y and the x, that y stays y all the time. That stays x all the time. They're static. They don't change. The y1, the x1, and the m, they do change. Okay, and the m is the, we're trying to find the equation of AE. So m is the slope of AE. Okay, so I'm going to find slope of AE. We said that was 3. Okay, like I said, y always stays y, x always stays x, but now I need my y1 and x1. And y1 and x1 are simply a point that comes off of AE. And how many points are on AE? Infinite. If I look at this point here, Sliding that across to AE. I can use any one of those points. Okay? Hopefully you realize that A is probably a good choice. E is probably a good choice. Even if I kind of looked at, I think, that one right there is probably a good choice if I wanted to use it. That one's a good choice. But all my good choices are integers, right? That point right there, terrible choice. It would work, but it's terrible. All right? So we want to use integers. And I know if I'm trying to find the equation of AE, A has to be on that line. So I'm going to use A. Okay, so the x by x1 is my negative 5. Y1 is this negative 6. Make sure you pay attention to your signs. Minus and negative is positive, right? So I change those. Now I'm going to solve for y. So I distribute my 3, I get 3x plus 15. Subtract my 6. I get 3x plus 9. And there's the equation, y equals 3x plus 9, that we need for AE. Is that all right? Okay. Now, I always get the question, how'd you know to choose AE? Or sorry, how'd you know to choose A? I didn't. I just chose a point that I knew was on that line. If you wanted to, you could have let your y1 and your x1 be negative 2 and 3. If I go y minus 3, okay, and then I've got my 3, x minus negative 2, okay, now it's going to change this math here, but that's going to become a plus, right? Now we'll have y minus 3 equals 3x plus 6. Add 3 to both sides. Do I still get y equals 3x plus 9? Yeah. No matter what x and y value you choose, as long as it's on AE, as long as it's on that segment, you're always going to get 3x plus 9. Okay? GeoGebra is nice because it does this for us. If I wanted the equation of AE, now I have to write a line here. I have to draw a line AE. So I click on A, click on E with my line tool. It gives me this. This is in standard form. If I right-click on it, I can put it in the form that we want, and I get 3x plus 9. Okay? Again, don't use that just to come up with the equation. Use that to know that your equation is true. Okay? With these questions that are very kind of step-oriented, if I would have messed up the slope on the first step, is that going to mess up part B, C, D, and E? Yeah. Okay? So as you're kind of answering part B, figure out a way that you can verify what you've done is right. GeoGebra is a way to do that. And as you find stuff for B, see if you can verify it. And as you progress, keep verifying your found information. We're now going to find the equation of BD. Okay, so BD. Okay, I'm going to use still y minus y1 equals m times x minus x1. But BD had a slope of negative 1/3, right? So I like to just, I know my formula is going to always have that kind of format. So I always fill in what I know. And now I need my y1 and my x1, right? I'm looking at BD. I got choices. I can use either B or I can use D, right? Hopefully Mrs. Coles or Mr. McCoy or Mr. Herr last year told you that if you have a point that has a 0 in it, use that one. Because when I go y minus y1, y minus 0, is that algebra really easy to simplify? Yeah. And then I put negative 8 in, which will become positive 8 there. Now it just gives me y equals negative 1/3 x minus 8/3. Leave it as 8/3. Leave it as negative 1/3. Because that's the easier thing to do. Is it going to take you more work to take your calculator and say that negative 8/3 is negative 2.666666 repeating? And then you can't really write that number down real well. But 8/3, you can write it as a concise value, even though as a decimal it doesn't terminate. So we got now the equation of BD. So what does this tell us? What are we going to do with these things? If you remember back to Algebra 1, when you started learning systems of equations, the first thing that you would have done probably is that you would see like a series of pictures, a series of lines. So let me just look at, in Algebra 1, you would probably provided those two lines. And you were asked, can you find where they intersect? Okay? And graphically, maybe you would, we're kind of zoomed out here, so let me zoom in a little bit. And you would look at those and say, well, it looks like they intersect around -3.5, y value of what looks like -1.5, right? And you did that a couple times, and you said, okay, can we now do some algebra that is going to convince us of that? Okay. So the first way you did is you took two lines, you graphed them, you saw where they crossed, and you kind of guessed at the ordered pair where they crossed. Then you started to do the algebra, the analytical, call it an analytical approach, okay? Using theorems and algebraic rules to prove that intersection. And if you remember, this was all part of systems of equations. Okay? Whenever you solve a system of equation, okay? And really whenever you solve any equation itself, the graphical idea is that you've got curves intersecting, curves crossing. Okay? And when you solve the equation, you're solving for the ordered pairs of where those curves cross. Okay? So when we solve a system equation, we're trying to find graphically the ordered pair where my cursor is. Okay? Now, kind of think, you don't have to raise your hand here, but kind of think of how you did this in your homework last night. Did you just look at it and say, it looks like -3.5, -1.5? Because a lot of people were able to do that and get the right answer. A lot of people, and one of the questions like the -5, -2. It's really easy to look at the problem, look at the picture, and get my intersection. And the end of course writers know that that's what a high school student wants to do. They know that a 13, 14, 15-year-old student, 16-year-old student wants to take the easy route, right? And they want to look at the picture, and they want to find the answer from looking at the picture, which is important to be able to do. But what they do then is that they write the question so that that thing doesn't intersect at a real nice value. They're going to write the question so that it intersects like right there. And now I don't know that to be -3.5. Maybe it's -3.4. I don't know it to be -1/2. It looks like more like -1.2 or something like that. Does that make sense? And they make you go through and find the right answer using algebra and not using recognition, right? Anybody, I give that to anybody in the 7th grade or 8th grade and say, can you find out where they intersect? All right? And that is not testing whether you are a 10th grader or 11th grader that is capable of doing algebra. Okay? So, how do we go about do the algebra then? We've done a lot of this already this year. We've got two equations. Two equations, y equals 3x plus 9 and y equals -1/3 x minus 8/3. What do you know about those two y's? They're equal. So what does that tell you about these two things? They're equal. So I'm going to write an equation that says 3x plus 9 equals -1/3 x minus 8/3. And we use the substitution technique of systems of equations to solve for x. I don't like that fraction stuff, so I'm going to multiply everything by 3. And so give me 9x plus 27 equals -x minus 8. Add x to both sides, I get 10x. Subtract 27 from both sides, I get -35, right? Divide both sides by 10. I get -35 over 10. They both have a 5 that divides them evenly. So I write it as 7/2. Pay attention to how they want your answers. They probably want it as a fraction, not a decimal. Okay? So I write 7/2. I like to write it as 7/2 because I know that when I plug things back in, I can multiply 7/2 by any number a lot easier than I can multiply any decimal by any number. Okay? So right now I have the x, and this is negative, sorry. We have the x value of where those two lines cross. We need the y value. Well, once you know x, Can you plug it up into one of these equations to find y? Does it matter which equation? No. Hopefully, you're efficient with your work and you think, it's probably easier to plug in the first one. So I'm going to go y equals 3 times negative 7/2 plus 9. Multiplying fractions, I go straight across the top, straight across the bottom. And we're going to add 9 to that. Now to add fractions, I need a common denominator, right? So that common denominator is going to be 2, so it changes that 9 to 18 over 2. And now I can add those together and get negative 3/2. And that's my y value. So x is negative 7/2, and y is negative 3/2. And that's the ordered pair for that point right there. GeoGebra won't do this as fractions, but it will give me the decimal negative 3.5 comma negative 1.5. Okay? Is that all right with everybody? The reason they do that, the reason they walk you through those steps is because the goal is to find distances. And they want to know what is the distance of, let's say, eventually that red segment. Not that one, but that one. If they want to find the distance of that red segment, don't I need both endpoints of that red segment? So that process of using system of equations is giving me that endpoint. And I need to be able to use that to come up with distances. So let's go ahead and do that. Clear this out. C was equal to negative 7/2 comma negative 3/2. All right. Remembering the distance formula. A couple different ways we've written it so far. Subtract your x's, square it, add to that your y's, square that. Okay. Or we could do it this way if we remember the delta x stuff. So we go delta x squared plus delta y squared. That's an alternative way of seeing your distance formula. Okay. But they want A, B. I'll do A, B, and D, E first. Those are a little bit easier. Distance of A, B, and then the distance of D, E. If I want to go A, B, I'm looking at these two ordered pairs, right? It says subtract your x's. What's negative 5 minus 1? Negative 6. If you square that, you get 36. Now I'm going to go negative 6 minus negative 3. Negative 6 minus negative 3 would just be 3, right? Or actually, it would be negative 3. But when you square that, you get 9. So that's going to add together, give me a radical 45, right? Well, it became problematic on this, and I got several emails last night, which is fine, okay? But how do I simplify that? I don't know how to do that. So we'll come back at the end, and we'll simplify these. We'll do them all together at once. You don't want to find distance D to E. So now I'm going to look at those two ordered pairs. Going through the same process. Negative 8 minus negative 2 gives me negative 6. Square that gives me 36. And then 0 minus 3 gives me negative 3. Square that gives me 9. What's that telling me about those two distances? They're equal. Okay. Now I want to go find distance between B and C. All right. Now this is where some of you encountered this, some of you didn't. So some of you found like your C to be actually like negative 5, negative 2. So you wouldn't have had to do this. But I'm going to subtract x's and subtract y's. But one of those x's is a fraction, right? Okay. And we can't use decimals because the end question says write your radical as a simplified radical. And simplified radicals never have decimals in them. So we can't do the work here with decimals. We've got to do it with fractions. So when I subtract fractions, what do I always need in order to subtract fractions? Common denominator. So I'm going to rewrite point B as 2 over 2, because that's still 1, right? And then negative 3 I'm going to write as negative 6 over 2. So now, when I subtract my x's, negative 7/2 minus 2 halves. That gives me negative 9 halves, right? So right now my x's are going to be negative 9 halves. We'll square that. Then we'll subtract my y's. Well, negative 6 halves minus negative 3 halves. That should give me negative 3 halves squared. Now I kind of wrote this a little bit differently than when we did this with whole numbers because of how we have to square fractions. You guys remember how to square fractions? Square both. Square the top, square the bottom. So negative 9 squared is 81. 2 squared is 4. And then I'm going to do the same thing with the 3 halves. So it gives me 9 over 4. Add those together. I get 90 over 4. Okay. DC then. Same procedure. Oh, didn't want to erase that one. D is going to be rewritten as negative 16 over 2, and 0, I'm just going to leave it 0. So now when I do the subtraction, negative 16 minus negative 7 gives me 9 over 2 again. Okay, it's actually negative 9, but it doesn't really matter. And then 0 minus negative 3 halves, actually gives me positive 3 halves. We'll square that. Does that still give me 81 over 4 plus 9 over 4? Which gives me radical 90 over 4. So you told me that A, B, and DE were equal, right? B, C, and DC are equal. So I'm going to go back to my picture. AB, which is, got some stuff here that's getting in the way. But that segment there and that segment there are equal. Okay? We just found that this segment here and that segment there were equal. And we also know that those two things were right triangles. So we have provided all the necessary work to show that those two triangles are congruent by what theorem? Careful, what kind of triangles are they? They're right triangles, so we got hypotenuse leg, right? DE is a hypotenuse, AB is a hypotenuse, and the other two segments are legs. Okay? So, we've done all the work. Does that make sense? To get to that conclusion of yes, they are congruent. All right? In the event of trying to simplify these things, let's just kind of walk through the different approaches you can use, because this is going to be very important. We got 10 minutes here, so I'll probably use most of that time to do this. But it's very important because when we start dealing with other triangles later on, we're going to spend basically an entire chapter using relationships that deal with right triangles and square roots that involve with right triangles. Okay. Once we see that, I think it's chapter 7. Once we see that chapter 7, those types of triangles come in every single section from chapter 8, chapter 9, chapter 10, chapter 11, chapter 12, 13, and they want you to always be able to use radicals. Okay, so there'll be a point in the year where you're thinking, will all these radicals ever go away? And they will, but it'll be like May 28th when they go away. Okay, so if you're a person that struggles with them, please hopefully take the time now before the stuff gets really hard and start using those numbers specifically in a lot of the questions, in every question. Take the time now to go refreshing your algebra skills, okay, to learn this stuff again. And I'll show you where you can find some resources here in a little bit. But we had radical 45, right? We want to simplify that. Radical 45 is a symbol for a number like 6.5-ish. Okay? We type in square root of 45, 6.708. Now that goes out to this too, okay? But that number actually extends on forever without ever repeating, ever ending, okay? So we can't really physically write that number down, right? in its entirety and be exact. If I write that out to 100 billion decimal places, it's still not really radical 45. It's something a little bit less than that. Makes sense? Okay. So we have to use symbols. It's much like pi. Pi is a symbol for a number that we know never ends and never repeats, right? So we can't physically write all those decimal places down, so we write it as a symbol. 45 is a symbol of that number. That's 6.7 number. Okay. But if I take that 6.7 number and multiply it by itself twice, it gets back to 45. All right. How do we simplify these things? When we simplify them, it's like saying like 2/4 simplifies to 1/2, right? If I have 2/4 of pizza, is that the same thing as saying I have 1/2 pizza? So when we simplify radical 45, I should still have something that expresses and provides the exact same 6.7 number. Okay? This is how you do it. What you're doing is, when you simplify radical, you're trying to find the largest perfect square that divides it. Okay? And divides it evenly. When I say divides it evenly, it gives you a whole number back. Okay? So what if I take a number, take 100. What can I divide that by to get the first or the smallest whole number back? If I take 100 divided by 100, I get 1 back, right? Okay? So that's really that's kind of trivial, not a big deal. If I take 100 and what can I divide it by to get the next smallest whole number back? 50, right? Take it divided by 50 will give you what? 2. Okay? And that's what we want to think about here. We want to think about a perfect square that will at least give me a whole number of 2 back, or has the potential of giving me a whole number of 2 back. That means that perfect square has to be less than 22.5. Does that make sense? So if I take 45 and divide it by 22.5, that's going to give me 2, right? So the numbers that are less than 22.5 are going to give me either 2 or something greater. And that's what we're looking for. So, in dividing or simplifying radicals, this is one approach. Take half that number, and that should then provide you a list of perfect squares that you could try. 1, 4, 9, and 16 are the perfect squares that are less than 22.5, right? Which of those, other than 1, because 1 is trivial, so never try that, but which of those divides 45 evenly? Does 4 divide 45 evenly? Nope, so that's not the one. Does 9? Yep. So that tells me that 45 is divisible by the perfect square 9. And if I divide 45 by 9, what do you get? 5. So what this tells me, what that practice tells me, is that 9 times 5 is the same as 45, and I've broken it down in a convenient way so I get perfect squares. Now you learned some algebra last year with laws of exponents and stuff like that. It said if you have a product underneath a radical, you can actually break it up to a product of radicals. You can do that. Okay? I'll show you at some point this year when we have more time why that works. We watched the video from, I think, 4th period, 5th period. I spent a little time talking about that. We ran out of time then. But now, you have the ability to say, okay, I have a perfect square underneath the square root. What's that going to give you? What's the square root of 9? 3. 3, radical 5. And you've now simplified radical 45. Okay? You probably talked about doing this way last year. 45. I know that divides by 5 and 9, and then you went radical 3 and radical 3, right? And then you circled those two and said, oh, those are go together, so they come out in front, right? But why do those go together? What's radical 3 times radical 3? It's that 9 right there, right? It's that largest perfect square that divided 45. And then you were left with radical 5, because of the idea that radical 5 is not a perfect square. Okay? If you're doing this with a fraction, because some of you saw fractions, let's say I have like radical 90 over 4. Okay? By the same logic, if I have a product under here, I can rewrite this as a product of radicals. But if it's a ratio, I can write it as a ratio of radicals. There's the law of exponents again. And now I can focus on that and say, okay, now this is 2 problems. It's a numerator problem, it's a denominator problem. The denominator is pretty easy, right? Square root of 4 is 2. Well, now 90, okay, you can cut it in half and get 45, and then start thinking about what are the perfect squares that are less than 45 that will divide that evenly, divide 90 evenly. Well, when I see 90, and you're going to see this with a lot of numbers, what number as a perfect square kind of jumps out at me? 9. Okay? 90 can be broken up that way, right? Okay? Now, that 9 becomes a 3. I get radical 10, and I get 2 there, right? Now, I would want to make sure that I look at that 10, and that all perfect squares are divided out of that 10. So take 10, cut it in half, you get 5, right? Are there any perfect squares less than 5? 4, right? Does 4 divide 10 even? No. So 10 is simplified. All right? There's a lot of ways, and it's because of how our algebra and our exponents and all that kind of stuff work, there's a lot of ways for us to kind of write and deal with simplifying radicals. My hopes are that you don't say that I'm going to focus on the factor tree technique, because if I start giving you numbers like that, that's going to be a pretty big factor tree, right? It's going to take some time, okay? My hopes are, as you see, well, that can be rewritten as 126 times 10. And now I can focus on the 126, right? And maybe do a factor tree of 126. And work from there, break things up, make things a little bit easier on yourself, save some time, and ultimately benefit that way. You're going to see, and some people are going to be like, well, I can use my calculator. You could. Some of your calculators